I have the links to that clearly. Like that's part of the plan, but the plan is after lunch. No, we have 7 and 11 stuff to watch. Okay, we're just gonna go detailed stuff. Yeah, talk about drivetrains.
Oh, we can.
Yes, John.
Okay. I thought we were talking about hard stuff.
I want drivetrains, though. I'm waiting for a call from a pizza man. All right, Abercheck has more stuff. They had some drivetrain ideas they want to talk about.
We go like standard, like 8-wheel tank drive, 4-wheel each side. Oh, West Coast drive, so all the wheels are cantilevered. I don't know if that means anything.
Let me go with
Leather on wheels and on the wheel. Okay, yeah, and then on the wheel.
All right, so to de-jargon some of what they just said. So this is the type of drivetrain they were talking about building. All right, so to give a brief explanation, just some of the words they were saying so you guys have some ideas. So what they referred to as a West Coast drivetrain is really just because teams in California built it a lot. So you have wheels that are actually, there's no other support rail on the outside here. And that's really that's one of the main distinguishing factors in terms of a West Coast drive. One of the things that's important, and one of the things a lot of teams don't realize, if you have 6 or 8-wheel drivetrains, not all of your wheels are on the ground at the same time if they're all traction wheels. In this scenario, the 4 middle wheels, the 2 here and the 2 on this side, would be on the ground while the other 4 are up off the ground. That may not make sense at first, but otherwise if you try to turn, these are going to have to scrape across the ground as you're turning, and it does not work very well. That's a really simplistic view of it, but that's the main reason. So the Kitbot chassis, if you choose to build it, is a 6-wheel version of a drivetrain that's like a tank drive, and its center wheel is dropped lower, so it's basically rocking on either the front 4 or back 4 wheels at any one time. All right. Anyone have any questions, things they want to talk about? We should be getting food here soon, if Domino's wasn't late, which they are.
So with that West Coast drivetrain, you're saying that the middle 4 wheels will be what's driving, and if ever you need to turn, the other 4 wheels will come off the ground?
The other 4 wheels are most of the time off the ground. They're only on the ground when you're accelerating. So if you're, like in a car, when you accelerate really hard, you get pushed back a little bit. Your robot will do that too, and it'll tip back if it's accelerating. But also in a pushing match, you'll get pushed back onto them as well. So it keeps you more stable because you're able to roll. Okay, Domino's is here. All right. Mary. Okay. Pizza's here, by the way. They're going to get it. Okay. Car. Pizza. All right, so we're gonna they're gonna get things set up over there, and we're gonna break for a little while so people can eat, talk about robot design some more. Then afterwards, we're gonna do a little bit of a comparison between a few different games, namely 2011 and 2007, so you can see how teams develop their robots. And then we're also gonna get into the new control system as well. Yes, okay, cool. Okay, all right, everybody. Thank you. All right, hopefully people have been fed, talked, we're all talked out. Thank you. Okay, you're welcome. Okay, all right, so prototyping So once we go through the design phase, so we have a list of all the designs we have all the things that we think we could possibly do. And just trying to, we haven't really talked about time scale very much, but you want to basically do those 1 through 4 pretty quickly. If you're not through to the point where you have done your brainstorming and stuff by pretty much the Monday or Tuesday of build season, you're going to be pretty close to behind already. So that means a lot of those first 4 steps are getting done that Saturday, and then if you meet on the Sunday, you have a little bit more time. If you don't meet that Sunday, that Monday and Tuesday is when you really want to be doing it. If once you're into that second week, if you're not already prototyping, you're not already getting things built, you're going to be pretty far behind. And a lot of it doesn't take that much time. It's better when you have the whole team together. So that's why we try to do it all on that first day when everybody's at kickoff. We can get everybody together in a big room, whiteboards, however you want to do it. Some teams do it with sticky notes, and they'll basically have everybody write down brainstorming ideas and put them up on the board on sticky notes, things like that. Whatever they can do to get as much contribution from people as they possibly can. And then once that happens, sometimes you want to give it a little bit of time to dwell as well. It helps if you go home, sleep on it. Your brain can process things a little bit different. You might generate some new brainstorming ideas too that way. But then at some point you're going to start prototyping, whether it's at the end of the first day, the Sunday, Monday, whatever it's going to be, you're going to start prototyping. So that means you're going to have some materials. A lot of times it's cardboard or wood, whatever it is. Most of the time it's not going to be stuff you're going to make the actual final robot out of. You don't need to spend a lot of money on aluminum and stuff to do your prototyping with. It doesn't have to be perfect. Some of the best prototype robots ever are made out of like plywood and 2x4s. But if you can get them to work, that's all that really matters. They just need to be somewhat functional. You can break a lot of the rules. They don't have weight limits because you're going to be able to refine them and stuff to make them fit within the size and weight requirements and things like that. And one of the things people don't do a lot of is actually iterate their prototypes too. When we were working in 2013 on how to shoot a Frisbee, we went through we knew we could shoot a Frisbee with wheels, but we didn't know the best way to do it or what type of wheel or anything like that. So we literally were just like, okay, we need to shoot it with a wheel. What wheels do we have? And we went through every wheel we had in our shop. We had people go into like RC hobby stores and buying RC car tires and shooting with those. I think we tried like rollerblade wheels. We tried all sorts of whole range of things that we thought were round wheels that might shoot a Frisbee well. We built some sort of prototype that we could just choose a variable and start modifying it until we found something that worked well. And then once you have something that kind of works, you keep improving it until you find flaws and make it better and better and better. And then finally, your prototype, you can take that and you can make a real design out of it. JVN stands for John V. Noon. He's also an employee over at Vex, but he's been doing robots for a long time. Has a couple different presentations on the engineering design process. The process we're going through was originally written by him. This is one of the engineering design process papers that he wrote about the steps in this order. And one of his quotes is, "You don't need to prototype everything, just the things you want to work." So you can put a lot of things on the robot, but if you haven't put a prototype of it at some point, the final one's probably not going to work because that is now the prototype, and odds are it's going to be broken. And a lot of the prototypes will never see the light of day. You'll prototype applications for things that make no sense. And I mean, I think at one point this year we prototyped some sort of weird ball deflector that was just, I have no idea what it was supposed to do, but it was never going to see the light of day on the robot. From there, you're going to be going into the point where you actually have to choose a concept. Depending on your team dynamic, this can get a little tough. Teams can do it in any way they want to do. We try very hard not to vote, because there's no real any basis for voting. It's just people getting emotional about they like things. It's much better when you can figure out a way to actually build consensus within the team, where you can actually reason out why one idea is better than another, some way that you can actually figure out quantitatively as much as you can and analytically to say, okay, this concept is a better method, we think we can get faster with this, or some way that there's a reason why we can build this over some other design. And you will have your team split at different points on different designs. One of the things that normally happens on teams, especially to get things going relatively quickly, is it may be someone on each like subsection of a group, and maybe someone over the entire team has some sort of design veto that says, okay, somebody has to make a decision at some point. Enough of the team is ready to go. We have 80% of the team on this design. We're going in this direction. Normally it's whoever your head mentor is, that type of person, but some student leaders have that power as well. There's a few different ways to do quantitative analysis of different designs. One of the ones I just want to talk about briefly, we're not going to go through it all that in depth, is called a weighted objective table. And basically you list all of the comparison criteria and you list all the different designs. So if we put out a bunch of different designs for claws that you could possibly use to collect an inner tube. The way, if for some reason, if all of your prototypes worked pretty well and you weren't sure which one to go with, you could make a reasonable weighted objective table for how to do that. This is one actually for a shooting game. Okay. So in this sense, we're basically saying what type of a single-wheeled shooter, or a double-wheeled shooter, or a turret. So like you'd have something that was able to turn and do other things, sort of like a tank. So you list the different criteria: complexity, accuracy, weight, number of motors, cost, time. You give them all weights in terms of where they ranked on like your specification tables. So you're saying if complexity is really important, or weight's really important, or something like that, then you score them all and you add up the score at the end. I can't. That's just how the PowerPoint's projecting it. It's real life on the PowerPoint, but it's not coming through there. The bottom last number is 115, but it's not important. The turret's bad. Don't build turrets. Most of the time, a turret's not the answer. It's too complex for what you get out of it. It kind of worked in 2012, but you could have done it in simpler ways too. Right, so the issue with these tables though is whoever's setting the weights for the criteria, you have to be very much not attached to any one idea. If you set the weights in favor of one of the ideas, it's clearly going to win. So you have to be very careful when you're actually setting the weights, because you can make it show whatever outcome you want to show if you're not actually trying to get a reasonable value out of it. So it doesn't always work, but you'll get into, like, anytime you're building something with a team, you're going to have people who disagree. You're going to have arguments. As long as you keep them civil and respectful, and you have people actually pushing out ideas and figuring out ways to make things better, and, you know, oh, maybe I don't quite like that, but maybe if we did this and tweaked it a little bit, or, you know, some way to compromise. There's lots of ways you can get to a final solution. It may be one different than the ones you thought you had before. And that also sometimes changes as you go through the detailed design, where you realize, oh wait, that doesn't quite fit the way we thought we did, maybe we need to tweak it a little bit more. Detailed design in FRC most of the time is going to involve CAD. Not all teams CAD. Abhishek left, sadly. He's from team 624. They're a very, very good team, and somehow don't CAD like nearly anything on their robot, and it boggles the minds of like everybody else, because we just don't know how they do that. But with CAD, with computer-aided design is what CAD is. You're able to basically take in all the parts from the robot, put them in a virtual space, and actually build them and make sure everything's going to fit together. You have all the volume, you have all the room, and you can really see mounting holes, configurations, everything in extreme detail before you actually build it. Even if you're building the robot with just a bandsaw and a drill press, CADing it all first is really important. It's actually more important in that sense, because you can get much closer designs, and you can actually know measurements and things beforehand when you have to actually do it by yourself, when you're doing all the measurements. A lot of little details people think they can push off to the end, and then it ends up coming back to bite them in the butt, just like not reading the rules. One of the bigger ones I've ever seen is people forgetting that they actually have to put a battery on their robot at some point. And they're just like, oh, we'll just strap it on somewhere. Then you end up with this 14-pound thing, 12 inches high on your robot somewhere where it shouldn't be, and then your center of gravity's all messed up, and it's not good. Design your battery into the robot, know where it's going to be, have a strap for it, know how it's going to be changed. All of those things go into a good robot design. Ground clearance can be really important. If you can't get over something on the field, or if you're too close to the carpet. Our robot this year is actually probably too close to the carpet. We eat up carpet. So like we have to clean it. It's really gross. There's carpet hair all over the inside of that robot. It's so bad. And we have a white robot. It makes it even worse. Motor usage is one of the details that we haven't quite hit on, but in the kit, it's not so bad anymore. It used to be a lot worse. You had very few motors that you were allowed to use in the kit of parts, so you were really limited on what you could do. Now there's so many options, and you have so much wattage in terms of motors that it's not too bad. You can kind of interchange motors all you want in what application you're doing, and you don't have too many problems. But still figuring out what's going to fit where, how much power you're actually going to need for any one application is pretty important. The wire path stuff is when you start getting into really advanced details. If you're in the CAD, if you actually know exactly which route all your wires and power distribution stuff is going to take, that's when you start getting more and more advanced to better and better robots. So you don't have, your arm cutting through right where one of the wires is supposed to be, that kind of stuff. Maintenance is the same way. When you start designing little details to where you can make it faster to change a motor if one blows, or a speed controller, or anything that you have to replace on the robot, if you're designing the robot to be maintained over the long time, these things are taking a huge beating now. Most teams are playing at least 3 or 4 times with all the off-season we have. That robot saw 8 events this year, which is just absolutely ridiculous. It's getting beat up and maintained. Like, we have to change parts on it constantly. We had to completely rebuild the entire collector system before remix because it was just shot. Like, it barely collected balls anymore. Yeah, it doesn't eject right now at all, actually. We should probably fix that. Okay, so if you want to do detailed design, I'll give you a few minutes. We're not going to take too much time on this. But if you want to go through and actually pick a concept, most of you already have one. But if people want to do reasonable sketches of it so we can actually see some designs really fast, we're not going to spend too much time. So we'll take like 10 minutes, try to make a few sketches of your robot just so you get some idea of how to draft stuff. People have laptops with CAD, feel free. We had people do that last year. Oh, the arms and lifts and things were able to move faster? Yeah. Being able to score quickly was really important. So not all robots could do that by any means. But especially at the high levels of the game, speed is very important. Like there's a lot of teams who could hang a single tube, but if you couldn't do it very quickly and under defense, you weren't going to win a lot of matches. Anything else that people notice about the game?
If someone was trying to score on the other team, if you could jiggle the rack and manage to try to block them at the same time, it'd be extremely difficult to actually try to get it onto the rack in the first place. So.
Yeah, you saw that especially in some of the Lone Star matches where that one was decided by a single tube that was scored on the rack the whole time. Defense won that entirely. In a lot of games, defense wins. The GDC, the Game Design Committee, has done a lot to push to where that doesn't always happen. But you can still a lot of times bring games back to defense, and stopping your opponents from scoring is always important. In 2014, you definitely had to put up a lot of points, but if you weren't doing things to prevent your opponents from scoring, you weren't going to win. Yeah.
So if you watch the finals of Einstein, which alliance do you think was the best alliance?
The red.
Blue. Blue scored more points. Blue consistently hit their autonomous, and they were just faster at scoring. What was red doing to slow them down?
Defense.
They were just playing defense, and they were playing little dirty tricks of putting tubes on their ramps, and they weren't hitting their autonomouses consistently. It's just purely defense and strategy won them the finals. So keep that in mind when you see these robots with these really fancy mechanisms and they can score lots of points. You can still win your matches. I know a lot of you guys are rookies and you're thinking, how are we ever going to compete with the Robonauts and the Kryptonites and all these really good Texas teams? Defense and strategy can win a lot of your matches.
Just a quick question. Were the opponent team, were the red team allowed to possess the blue?
Mm-hmm. Yeah, you could possess other team's tubes.
Oh.
Yeah, the game piece was a game piece in that game. There was no rule against. As long as you were only possessing one, you were fine.
Oh, okay.
Oh, yeah.
Were you allowed to just like take the tube from them? Like if they had it in their claw, if your claw is more powerful, could you just rip it out of their claw? Were you allowed to do that? 'Cause I don't know what.
You weren't allowed to damage the game pieces, so it was, yeah, you wouldn't want to actually grapple the tube at the same time, as far as I remember. Yeah, the one was popped.
If the referee sees you do it multiple times, this is like many rules, if they feel like you're doing it intentionally, you risk disqualification or some serious penalty. So that's just kind of a general thing in all
Right.
these games. There's a rule, and the referee is kind of watching for it. You do never want to be at the whims of the referee's decision.
Right.
That will never win you matches. So that sort of stuff you got to be real careful about.
Okay. Anything else directly about the 2007 game? So we're going to talk a little bit about how iteration happens over years as well. So all of those robots, I can guarantee you went through numerous changes. Even actually, Pink's robot from that year is an interesting one when we talk about iteration. So their robot, the Pink robot that had that arm that extended in and out, it kind of was low to the ground. They started building that robot, basically the same thing, in 2005. They built roughly as close to identical robot as you could possibly imagine. It was literally the same drive base, had the same type of telescoping arm, and then it just had a different manipulator on the end to grab the 2005 game piece, which was big PVC pyramids. And then they used it again in 2007. And they even used it again in 2011 to grab the other inner tube game, the triangle inner tube that we had sitting around here, which I'm about to show the game animation for. So they went through and said, all right, if we can, we like this, we know it works in some way. If we can adapt it to another game, let's just keep improving it, make it a little bit better each time, and keep using a similar design. So in 2007 and 2011, First has done this a few times where they basically, it's never the same game, but they'll recycle pretty large elements of it. So 2007 was an inner tube game that we've been looking at all the time. 2011 was also an inner tube game. There's going to be some key differences that we're going to look at. So while we're watching this game animation, start looking at ways that this game is very different from the 2007 games and why.
Two were to place during this period.